Uh, this is relearn something. We are going to be covering the expected value and mean and variances. I think these are kind of fundamental things in probability. I think it's also a philosophical part in this theory. And they are important also. So the expected value. Let's start with this, describing it. So the formula is here from E1 to N Y E P E, right? P is the probability and Y is the uh, let's what we can say. Mm, what can we say? Random variable? Nah, bigger Y is E. This is our random variable. This is the area occurrences in the random variable. Okay, occurrences. So actually, we can describe it like that. Expected value is average in the average value of the random variable. Okay, and we calculate it by the multiplying the occurrences by the probabilities and summing all the possible outcomes. And the random variable. So let's calculate random variable. So we have. I'm going to be using the example from network. So we have a wireless Wi-Fi network. Okay. So this Wi-Fi network can fail one time in probability P1, two times in probability P2, and it may not may not fail ever in P3 with three possibility. So our expected value for the failing time for our network is calculated by 1 times P1 plus 2 times P2 times plus 0 times P3, which is equal to 1 times P1 plus 2 times P2. So we are expecting our network to fail P1 plus 2 P2. So this kind of a trial. I mean, how can we use this idea? Uh, let's say we are producing a wireless device, and we produced like 1,000 times. Like we produced 1,000 of them, and we just started to test them, and some of them failed one time in with P1 number, and some of them failed P2 with two times, and some of the and P3 of them has never failed. Okay, so by this experience, by these trials, we might expect it. Yeah, when we set up this wireless network on wireless device on let's say on a building, we expect them to fail 1 plus 2 P2 P1 plus 2 P2 times failing. I mean, that's an guessing value. I think I hope my explanation is clear. This is very useful when you. This is very useful when you have an experiments, when you have trials, and you can use these trials as a sample space or a sample space for random variable. You can use those as probabilities, and you can expect them. You can expect your products failing possibility, and you can guess how many times it can be fail or it may not fail, or what is the probability of failing, and you can calculate this by this expectation. However, I think there's an intriguing question right here, lies right here. Let's think a dice roll. You know, having one, times failure, having two times failure, having zero times failure is kind of like that. Let's think a dice roll. So we have a dice having one, two, three, four, five faces. Let's say it has five faces. Okay, and each face has a same likelihood to get as a result of dice, as a result of our dice roll. So we have probability of 1 over 5 getting this, 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 and 1 over 5 getting this. Okay? So what will be our expected value by this? So 1 over 5 plus 2 over 5 plus 3 over 5 plus, I mean 1 times 1 over 5, 2 times 1 over 5, plus 3 times 1 over 5 plus 4 over 5 plus 5 over 5. So from 1 to 5, when you sum them up, this is 15 over 5, which is equal to 3. So you expect your dice roll, when you dice, when you roll the dice many times, you expect to get more, more, and more and more threes, right? Let's say you roll the dice, let's say 1 million times. Okay? And you are expecting that by this idea. So you're expecting from big chunk, not let's say big chunk there, but you will get some ones, some twos, some threes, some fours, some fives, and you're expect so you the number of trees you get is would be much more than the other things, right? But is it actually correct way to think? I'm not sure about that. However, as far as my research, they say that it's accepted as calculated like that. However, when you think about a dice roll, the number on the faces are doesn't matter actually, right? Hmm? Yeah, it doesn't matter. I mean, having one on the faces and having two, five in the other face doesn't mean anything in the universe of the dice. I mean, it doesn't matter for dice. I mean, these fives and ones and twos and fours doesn't have any magnitude. It's just a representation of a face. They are just a representation for a face. So how come your expected value for a dice roll will be 3 when you have a dice roll having 6 faces, and if you assume that having all of them having same possibilities, so your expected roll will be 3.5. So you are saying that by this, when you roll 6 faces dice, let's say a million times, so your likelihood of, so you will get three and four threes and fours, more likely than the others. So I'm not sure about this actually. Why? Because like I said this doesn't have any meanings in the dice roll universe. I think you should not calculate the expected value of a dice roll like that. I think you cannot calculate the an expected value for a dice roll. Why? Because these are just the representations. These doesn't mean anything in the dice roll universe. In a dice universe, it's just a representation of faces. Okay. Well, let's say instead of having these numbers, let's say we had just different shapes like square, triangle. I don't know the English word for this. Diamond? I don't know. It's just a card shape, but I guess it was a hexagon. I don't know. What was it? Octagon? I'm not sure this. Let's say you had this. You put them here. So, okay, you put these on those faces on the dice roll. So, expected, so calculate the expected value for these dice. Okay, you cannot, I mean, which one will be one? Which one will be one? Which? It's a question mark. So, as far as I researched, I made a research, all of them calculating right here, like that. Okay, a result of an dice roll. However, in the universe of the dice, these values doesn't matter. Okay, these values doesn't matter. I don't know. I hope I could write a simulation for a roll, but I'm not sure. So, however, when these magnitudes are important, you can calculate it. I think you can calculate it because in this universe, we these are important. These magnitudes have values. I mean, having one failure and having two failure, these means actually means something because when you have one failure, you had less failure compared to other devices having two failures. These magnitudes have values. And you are using the magnitudes. You know these magnitudes are important. I mean, having one, two, three, four, five does mean something, and their magnitudes affect the sum. However, in this here, I'm not sure about that. So this is a big question for me. So you can use when can you use the expected value idea? When can you use? I don't know if there's some mathematician right here who if some mathematician comes up to this, would you please explain it to me? I'm not about that. However, all the things that I find in the forums or and things like that, they are saying that you can calculate the expected value for a dice roll like that. However, actually, I'm not buying that because these are the just representation of the faces. These numbers are just representation for faces. Their magnitudes doesn't important. I mean, in the universe of the dice, having five and having one is equal because they are representing something. However, when you use one, two, three, five in a numbers universe, by the way, when we say one, two, three, four, for example, when we think about blocks, we can say we have one block, we have two block, we have three blocks, something like that. But in here, it doesn't matter. Okay? Because these are just things. And also in here, these values have importance because their magnitudes matters something. I can relate calculating it by that with calculating, for example, for expected value for this, because it makes me reasonable because this magnitudes has importance. I mean, this means that have, you did not have any failure. This means that you have failed two times. This means that you have one time. You have failed one time. So, however, so in this universe, it's important because it represents some things. It represents the amounts, the magnitudes are important. However, this doesn't mean any magnitude. This doesn't represent any magnitude, any amount, anything like that. So I'm not sure. I'm not sure about this idea if of calculating the dice roll like that, any metaphor dice roll like that. I'm not sure. I'm just saying. However, when we toss ahead, it's another thing. I can relate this much more. Let's clear this. I can understand this idea. I'm toss a coin. So you said that head is one and tail is zero. Okay. Why do we say one head and tail is zero? Why? Because we just said. Because I think in we are interested in our likelihood of having head. Because we are interested in the heads, not the tails. Okay? So in the universe of having head, or this one let's say have a probability of pH, this one have probability of PT. So this one be PT plus zero times pH plus zero times PT. So this is pH. However, if we are interested in having tail, okay, our expected value will be PT. I mean, it depends on what you are interested in, what's your question. Which is why I can relate the expected value for this. For example, you toss a coin, let's say, how many times? Let's say 1,000,000 times. So what would be? And you get each amount of it. Okay. So you will get what? H over 1,000,000 possibilities. When you consider your sample space as this, and you can say that our probability of getting hit is H over 1,000,000, which is pH. Let's say pH. So expected value for your toss coin. So if you toss a coin the next time, you can expect them to get pH, the number of pH. What is it? This is what it will give. You're assuming on the probability. So you are assuming that you have pH probability of getting heads. So this is an interesting concept. Yeah, so you can use expected value to get, in my opinion, by the way, is like I said in the first video. I'm going to repeat it in this video here. I am trying to understand, relearn things, trying to learn the ideas behind it and discover these ideas. Why? Because I didn't understand the ideas. I mean, they haven't mentioned the ideas. Some things I understand. Yeah, I thought that yeah, this is reasonable, and I sometimes I couldn't find the ideas. However, I'm trying to get the ideas right here. I mean, it's just easy to say that you can count the expected value of a dice, blah 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 like that. However, it just doesn't seem rational to me because you, as I said, these phases doesn't have any magnitude. These magnitudes are not important in the event of event for a roll. This is much more reasonable for me because you are interested in getting heads in this. Okay, when you calculate it like that, you are interested by the view of getting heads. This is much more reasonable for me. I can relate this idea much more than an average value of a dice roll. A dice roll. Uh, because you, like I said, and the example on the network failure. So you get the one times failure, to one two times failure, okay, and the amount of the and the result will be the possibility of your network failure. Like, I mean, let's say you said you trialed with 1 million wireless mobile devices, and zero times failure is, let's say, k, one times is l, two times is m. So what will be k over 1000, 1 million, I'm sorry, plus l plus 2m will be actually your expected value. So you are generating a possibilities, I mean not possibilities but probabilities for your, what's what we can say, for your event, for your sample space, for your future thinkings by this expected value techniques, in my opinion, right? Right. So, for example, let's further thinking. Let's do a further thinking. So let's say one, two, three, blah 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 blah, and failures comes to like 1 million times. One keeps always failing. Okay, 1 million times. Okay, blah 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 blah. So let's say that your expected value gets bigger than one. What does it mean? This is another question in the event of here. Can it be like that? It can be. So your probability is bigger than one. There's another question. So we developed an idea if you are assigning a possibility value to your device or event or something like that. However, it's failed again because it's not a possibility because it can be more than one. So you have 1 million. Okay, if every time, if some of them have 1 million times, so what would it be? You will get over that one. And I mean, not just that. I mean, uh, if all of them fail to 10 times, I think the expected value will be bigger than one, right? 10 times 1 over million times 1, yeah, it will be 10x. Your expected value will be 10. So you expect your device is to be failed 10 times. So this result in a different opinion. So we are trying to find the idea behind the expected value. We describe it by the average value by from the book. We describe the expected value as long run average of a random variable for occurrences. The book described, I'm going to be reading as same as possible. Long range value of the random variable over many repeated trials or occurrences. This is it. Okay, that's it. So what can we do with the expected value? Long range average value for a random variable of a random variable over many trials. I mean, the dice things is a tricky things. The dice thing is tricky. Why? Because the face things. The face things. Because of that, I'm not sure. I'm not sure you can use. Yeah, and I mean, when the magnitudes of the numbers are not important, I'm not sure you can. I'm not sure about whether you can use the expected value like that. Ah, okay, not the possibility. Of course not. How many times you will get? In the event of a toss coin or a Bernoulli variable is whether an event occurs or not. It's either 1 or 0. There are two possible values. A toss coin is a Bernoulli random variable. So, in the universe of a Bernoulli random variable, a toss coin means tossing a coin means the expected value means your likelihood of getting the interested value. Interested value. I mean, when we are interested in a head, we are assuming we are using this as our probabilities. I mean, our probability of getting head. However, when we interested in like this discrete random variable, 1, 2, 3, 4, 5, 10, blah 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 blah, it goes to infinity. We are interested in getting what? The average value of get occurrences. Okay, this is much more distinction between them. So I mean, in a discrete universe or a continuous universe, you cannot use expected value as the average occurrences. You can use as average occurrences. However, in the universe of a Bernoulli random variable, you can use it to get the probabilities. I mean, I guess Pearson made a trial like that. He tossed a coin like 12,000 times or something like that. I mean, he tossed a coin like many times and he recorded it and find that, I mean, probability is similar to 1 over 2, which is why we are uh, exacting probability of a task coin will be 1 over 2. I'm sorry, I just snorted. But it's getting a little bit late here. I'm sorry, it's not a professional thing for someone who mentions some important stuff. However, they are important stuff actually, but not in the dice roll universe. I'm still not like it. I will search up the idea behind that. Why? Because it's important. I mean, this is philosophical, and how do you understand? It's a question about it's a philosophical question. Important thing. on how do we understand the world. So let's clear the page. So mean is equal to expected value, by the way. We describe expected value as two different occasions. When you have continuous or discrete random variables, right? You can you think like run average occurrences. In a Bernoulli case, you can think like probability of getting interested outcome. Let's not value the outcome. Yeah. Yeah, toss coin, we are interested in getting head. Toss, we are interested in head. Then our expected value will be pH. However, how do we calculate pH? By using expected value. I mean, we are using EY to get pH in Bernoulli random variable. However, the book described it as P will be our EY. Yeah, that's true, but this is different. This is different. I'm using EY to get pH is different. Using P to get EY is different. Okay, it's different, man. It's simply different. I understand this. This is much more reasonable to me. I mean, using EY to get pH is, yeah, rational. I mean, you don't know the probability of getting head. If you try infinite times, then you get it. However, is it possible for you to get infinite amount of times? No. So you will use EY to guess the probability of getting head. However, the book says the pH is our EY. I'm not sure. I'm not the expert, but yeah. In continuous, it's a different thing. Uh, it's from the calculus. You can calculate by the calculus. I mean, uh, when you graph it like that probability density function, let's say it's not true. It's not. It's not. Oh man, it's not. Let's put this again. Let's say this will be. Let's say this is our probability density function. How can you calculate it? How can you calculate it? So you are dividing and calculate. I remember from the calculus one, but I forget. You are dividing this by the form function. Is it something like that? This is yeah. I think it's from the integral comes. It comes from the integral, I guess. Uh, yeah, you are using the integral of this function and dividing it to the function itself. Was it something like that? I'm not sure. I'm not sure. I don't remember this idea, but it's actually cool. You can. use, let's not think about generous, but let's think about, let's try it. Let's try to rediscover it. Yeah, we have our function again. We are trying to guess the expected value of the function. Okay. And let's say our function has finite function. Okay. What was our formula for this? 1 to n y times pi. Right? Yeah. Actually, the relation between EY and pH is something like that. When you think about this case, it's something like that. I mean, you are trying to guess the pH by this, by the EY. Yeah. No, but not by the EY. No, 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 no. It's different. It's different. It's different. Yeah, in this case, it's different. No, no, it's not true. It's not true at all. Uh, Man, the formulas are just keep make things are worse. Why? I mean, it could be used in a Bernoulli event. If you're interested in one value, you are assigning a value to it. So the other things. So the other things will be like. So you will get the EY. Yeah, yeah, man. You will get the EY as PH. Yeah. I mean, the the clear definition of a term is very important. If you don't describe it correctly, then you will get a better result. I mean, there is a mess up. If you don't describe it clearly, then there's a mess up, man. Yeah, yeah. When you think about the Bernoulli, when you say that there is average, long run average of the occurrences or trials, when you think like that, so you're, and if you are interested in the heads, so you will get EY. And you can use this EY as the probability of getting heads. Why not? Because you tried many times, and you get X amount of heads in tossing Y times. So you can use X over Y as your probability. I'm cool with this idea. However, when you formulate it like that, there's a mess up, man. Just keep it simple. Don't brute force it. Just keep it simple. You know the idea. You can tell you can you can tell these things like this. You can tell this. You can we can discuss over it on these things. When you don't discuss on these things, I feel like a slave. I mean, not just like a slave, but a robot. Oh, I feel like I'm having a whatever. In continuous random variable. So this is important. Okay. So you have random variables like these, right? So this is our random variables, and this is our probabilities. Actually, this and this are probability. this and this our probability. This and this here is our probability, right? Huh? Actually, this is our probability density function. This here is our probability. This straight is probability for just one thing. However, we cannot calculate the area of one thing. But what can we do? We can calculate this area. Oh, no, I remember. However, when you when it says yeah, when you can have a function like that, this is the average, and from here to here, you can measure up this. You can measure this. You can divide the area over this length, right? Because areas are the sum of these lines. However, when you have any function like that, length, length goes from infinity to infinity, right? And this is our random variable. And you are using this area. This is a probability. This is a probability. This is a probability. So how? I mean, I'm not sure how can we do this. How can we calculate this? I'm not sure. I am not sure. Definitely. So the book says you calculate in an appendix. I can check it. Ooh, I mean, we talk about the expected value for a long time, right? The mathematical things are not important. I mean, of course, they are important. How to calculate this? How can you calculate it? I'm still not get over with the so. I'm feeling like it's so fucking so much true. I'm. This feels like in the event of a dice roll. So variance. So this is a measurement method. So aim is how disperse. I'm not sure how spread our random variable is. I mean, we are trying to how spread our random variable is. So we are calculating it from how spread, how distant, not distorted, but how spread our random variable is from the point of mean. I need to say mean mu. This is not m mu. I cannot write mu, but this is mu, not m. Ay. So y minus mu square is our expected value. How do you calculate that? It's another question. Man, it's another question. Yeah, I mean from u1 is mu square. That's it. So was it right? So you can stick mu. You want to, can you do these things like in mathematics minus one and square? So you can stick. Can you stick this in here? Can you not? I'm not sure. Mm, yeah, I guess that's true. I'm going to check it. I'm not good with formulas. U squared times pi, by the way. I forgot the pi. Oh my, yeah. Can you put it in here? I'm not sure. Why? Because it also depends in here. I mean, this is separated calculation from the whole things. I mean, you do this. You should do this first, then you do this. Then for each calculation, you calculate this again. However, the result will be always same, so you can just put it in here. Whatever. So this is the variance. I mean, we are trying to understand how our random variables is distributed. So thank you very much for listening. Thank you very much for listening my naggings about ideas and mathematics. I mean, I might sound a little bit overconfident or a little bit narcissistic, but I think my questions are valid. Yeah, the expected value of a dice roll, I'm not sure. You can replace numbers with symbols and you will still get the same likelihood to get these symbols. And the number of the magnitudes of a certain of a place is not important. I mean, I hope. I mean, maybe we can write a code for from Python to simulate that thing, but I'm not sure. Can we? We can. We might not. I'm not sure. I don't know, but maybe I could search it up. For whatever, I'm going to be searching the idea of a rice roll and expected value and variances. Maybe we can recap these things. I'm going to be searching these things, and if there's an update, I will update you. If there's not, I will say, yeah, these are still blunt. These are not questioned yet. So thank you very much listening again, and I hope you will have a great day, week, and life. See you next time.